said, finding equations of tangent lines and finding slopes of tangent lines, we will be doing that all year. And then also a huge application of that, a huge application of the slope of a tangent line is finding velocity of an object at a specific instant in time. So not finding an average velocity, but if I want the velocity at 3 seconds, finding what that would be. So then we have the velocity problem as the second part to this first section. So average velocity, I have here that there's a specific formula that we use to calculate average velocity. If you think of the distance formula, that distance equals rate multiplied by time. So if we solve for the rate is equal to the distance divided by the time. So I'll just write that out in actual words. So average velocity, because that would be your rate, and this would be average velocity over a time interval. So if you want to add that into over time interval. So this would be equal to the distance traveled divided by the time elapsed. So the length of the time interval. So if you are asked to calculate the average velocity, for example, from 3 to 5 seconds, also over a 2-second time interval, that's the formula you can use. So we have a formula for that. In calculus, though, you're going to be asked not only to find average velocities, but also an instantaneous velocity. And I'm just going to put instantaneous in parentheses here because anytime you're just asked to find velocity without any word written in front of it is assumed to be instantaneous velocity. If they want average velocity, you will have the word average written in front of it. So anytime you are just asked for velocity, it's instantaneous. But instantaneous velocity, there isn't a formula, so I'm just going to write what it would mean. This is going to be asking you to find the velocity not over a time interval, but at a specific instant in time. So like I said, velocity at 5 seconds, or they might even say after 5 seconds. So again, it's all kind of making sure you understand the wording of a problem and then knowing what to do with that. So we're going to get right into the first example. And it says, suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto, which is 450 meters above the ground. And then it says, find the velocity. So again, it's not saying find the average velocity, it wants the velocity, so instantaneous, of the ball after 5 seconds. And even if it says after 5 seconds, you're finding the velocity at 5 seconds. So then it knows after that how fast it's traveling. So I did include in here, because you wouldn't be expected to come up with this on your own, the equation that represents the distance in meters fallen by a free-falling object neglecting air resistance is this function here. So this is the function we're going to be using. F of t is equal to 4.9 t squared. You will see in calculus, maybe, I don't think it's the same in physics. I think they use x. So in calculus, you'll see s represent position. So like a position function will be s. Velocity v, acceleration a. So, but I think am I right in that physics uses x for position?
Yeah.
Or displacement? Yes. Yeah. Position, displacement are kind of interchangeable words for calculus. And then t is measured in seconds. So distance is in meters times in seconds. So I have on here, I just included this with the example. Difficulty in finding the velocity after 5 seconds is that we are dealing with a single instant of time. We're dealing with t equals 5, so we don't have a time interval. So we can't just use this formula to answer the question or use the formula one time. So kind of channeling back to what we did yesterday, because we had that same issue yesterday. We wanted the slope of a tangent line, but we only had one point. We didn't have a second point. So it says we can approximate the desired quantity. We can approximate instantaneous velocity by computing average velocity over brief time intervals beginning with t equals 5 seconds. and then making those time intervals shorter and shorter and shorter. So I am going to, I'll just do 3 here. So I'm first, I said yesterday, I know I started, like our x coordinate was 1, and then I started with an x coordinate of 2, but then I said in calculus, really being 1 unit away from something is actually really far. So I'm going to start with a time interval that's only 1/10 of a second. So starting with t equals 5, and then my second t values, maybe I'll say t sub 1 is 5, and then t sub 2, I'll have be 5.1. So we're going to calculate the average velocity over this time interval. And again, this is a time interval of 1/10 of a second. So it's a very, very short time interval. So what I'm going to need to do to calculate average velocity is I need to find the distance traveled, so the change in distance over the time elapsed, so the change in time. Average velocity is really a slope. I can think of these as ordered pairs. So these would be like my x coordinates. I can substitute these times into my position function here, or displacement function here, to find the position at 5 and 5.1 seconds. So when t is 5, the position, so I'll put s of 5, which my s's look like 5s. Yep. So again, I'm substituting it into this function, the s of t, so I'd be calculating 4.9 times 5 squared. So at time 5, its position is 122.5 meters, or displacement. And then I'd be finding s of 5.1, so 4.9 times 5.1 squared. I'm going to keep all decimal places here, 127.449. Okay, so like I said, you can think of these as ordered pairs, and calculating an average velocity is like calculating a slope. Change in position over change in time is going to be the change in y over change in x, essentially. So I would have 127.449 minus 122.5 over 5.1 minus 5. And that would give me 4.949 over, that's 1/10 of a second time interval. So that gives me 49.49. And this is an average velocity, so the units be meters per second in this case. So that average velocity for that 1/10 of a second is 49.49 meters per second. Sam?
I might have missed something. I thought the instantaneous velocity was the one where you have a time elapsed, and there's a 10th of a second. I was just wondering why.
This is not our final answer. Yeah, this is only part of it. So the issue is there isn't a formula for this. There isn't a formula for instantaneous velocity. We have a formula or a way to calculate average velocity. So we are approximating the instantaneous velocity by finding average velocities over brief time intervals that are going to get closer and closer to just that specific instant. Yeah, so this is only one step. We're not done. This isn't our answer. So now that was a 1/10 of a second. I'm going to shorten that to be 100th of a second. So I'm going to start at, I'll say t sub 1 is 5, but now I'm going to use t sub 2 to be 5.01. So I'm shortening my time interval to be 100th of a second. And I'm going to do the same thing, calculate the average velocity for that time interval. So I already know my displacement or position at 5. So I need to substitute in 5.01 into the function to find that that position there. So I have 4.9 times 5.01 squared. And again, I'm going to keep all the decimal places. So this would be S of 5.01 is 122.99049. So my change or my displacement, my change in position is 122.99049 minus my position at 5 was 122.5 over 5.01 minus 5. So my displacement is 0.49049 over, this was a 100th of a second. So that would give me 49.049 meters per second. All right, and then I'm just going to do this one more time so you'll kind of see how close I get to 5 because I'm kind of using the same distances from yesterday, the last 3. So I'm going to shorten that even more and do 1,000th of a second. So I'm going to go from t sub 1 equals 5 to t sub 2 equals 5.001. This would be the last one that I do. And it is important, if you have this type of problem, it is important, I'd say, that you do at least like these 3. You obviously can't just find 1. I would say don't even just stop at 2. So I'm finding at least 3. Again, what we're going to be looking for is the limit. You might already be able to guess what that limit's going to be, but you should have at least 3 calculations done. So unless the problem specifies more than that. So again, I already know my position at 5. I need my position at 5.001. So 4.9 times 5.001 squared. I'm just going to write this as part of my calculation here. So I am calculating this.
I just need to go to the bathroom. Sure. I just want to make sure they know everything.
This is the position at 5.001. So again, I kept all the decimal places, 122.5490049 minus 122.5 over 5.001 minus 5. So we have 0.049049 for the displacement over 0.001 for the change in time. So that'll give us 49.0049 meters per second. All right, and then we could obviously shorten that and do 1/10,000th of a second if we wanted to. Probably not necessary. So then I have here, so it appears as we shorten the time period, again, all these time periods start at 5, and as you shorten that time period, the average velocity is becoming closer to what? 49 meters per second. So the instantaneous velocity when t equals 5, or the instantaneous velocity at 5 seconds, is defined to be a limiting value, or the limiting value of these average velocities over shorter and shorter time periods that start at t equals 5. So I'm just going to highlight this, because again, this is the idea you need to understand. Instantaneous velocity is a limit of average velocities. So thus, the velocity after 5 seconds, which would be the instantaneous velocity after 5 seconds, is 49 meters per second. Okay, and then I have this written below. I have it written in words. Well, actually, I don't have the limit written out here. I have a comparison to what we did yesterday. So I already said average velocity. Calculating an average velocity is calculating a rate of change, which is a slope. So slope is a rate of change. Average velocity is a rate of change. They're both slopes. So I could have given you the same problem yesterday, but instead I wouldn't have given you a context behind this function, I just would have said estimate the slope of the tangent line at s of t when t is 5. I could have phrased that the same question that way, and you would have worked through it the same way. These would have been your secant slope. 49 meters per second would have been your tangent slope of your tangent line. So again, something you need to understand from this is that anytime you are asked to find the slope of the tangent line, if that function represents position, you are also then finding the instantaneous velocity of that object at a specific time. So the slope of a tangent line, an application of that is velocity. So two big ideas. You will see in calculus that a lot of ideas merge like that. It's important that you understand they mean the same thing because you could be asked 5 different questions, say, where for all 5 questions you do the exact same work, get the exact same answer, but again, the question is asked a different way each time. So it's important that you understand that those ideas do mean the same thing. So slopes of tangent lines, an application of that is instantaneous velocity. You find those the same way.